Alright, so as usual with the 3D trig question, we start by drawing out the triangles that are involved with our 3D diagram. So in this question we've got a tower, which is represented by the line XT. So X is the base of the tower, T is the top. We've then got a point P that's south of that tower, and Q that is east of that tower. So our triangle TXP is going from the top of the tower to the ground and out to a point P that's on level ground. And our angle of elevation is 20 degrees. And then we have our second triangle, which is also from the tower to the base of the tower and then out to a second point Q. And the angle of elevation from Q is 35 degrees. Our third triangle is our bird's eye view. So looking above this diagram, we would see that the tower is at position X, P is directly south or due south of that, and Q is due east of that. So that's our third diagram, our third triangle, which is also right-angled because we have a south and an east. Alright, so our first question asks us to find, use triangle TPX to show that PX equals H tan 70. Now, if you have a look at the triangle that we've drawn for this, you'll see that we don't have 70 in our diagram. So the first thing that you must realize is that the 70 comes from the second angle in this, or the third angle I should say, in this triangle. So the 70 is there. While we're doing that, in the second triangle we'll also be needing to find that angle there, and that is 55 degrees. Okay? We can see that by looking at part 3 where it uses 55. Alright, so part 1 is in triangle TPX. We're using the angle 70 and we're finding an expression for PX. So that means we've got tan 70 is equal to opposite, which is PX, on adjacent, which is height. Alright, so to get PX on its own, we're multiplying by 8, so we get H tan 70, which is what the question asked us to do. Part 2, find a similar expression for the length of XQ. Okay, so in the same way as what we just did, but using the second triangle, in triangle TQX, we've got tan 55 this time is equal to QX over the height. Rearranging to get QX on its own, we get height times tan 55. So that's part 2 done. Part 3 is hence show that H is given by that expression there. So part 3 is now relating the side that we found here, PX, is now this length here, and QX is now this side of the diagram. And we have our third side, 40. Since we have a right angle triangle, it makes sense to use Pythagoras for this question. So we've got 40 squared is equal to PX squared plus QX squared. So if we replace PX and QX with what we said they were equal to, PX was H tan 70, so that gives us H squared tan squared 70. QX is H tan 55, so that squaring that gives us H squared tan squared 55. We then need to get the common factor of H squared out, leaving us with tan squared 70 plus tan squared 55. Okay, dividing by the tan 70 and tan 55, that means we're going to have H squared left on its own. I've just reversed the equation, okay? So 40 squared was on its own. We're now dividing that by tan squared 70 plus tan squared 55. And our final step to get it to look like as the question asked, first thing you'd probably see is that the 40 squared has been changed. 40 squared is 1600. That's where that comes from. Then we've got the tan squared 70 plus tan squared 55. And because we are finding h, not h squared, we then square root that. And that's part 3, matching up to what the question asked right there. Finally, hence find the value of h, correct to the nearest meter. So using your calculator, we do the square root of 1600 over tan 70 squared plus tan 55 squared. Okay, so we get to the nearest meter, we get 13 meters. And that's done.